Hi there, welcome to a video series on what I like to call obnoxiously complex looking trig identity problems. In this particular example, I want to show you how to prove that the left side equals right side for this monster, which looks really bad at first, but is actually not that bad, as long as you have an understanding of common factoring the Pythagorean identity. So what I normally recommend doing is starting with the most complex side. In this case, it should be pretty obvious that the left side is more complex than the right. There's a bunch of sine x's and cos y's and squares and plus signs thrown in there. What I want you to do is just kind of take a scan through the left side and just see if you can pick out any common factors. You can see that each one does not have a common factor with the other, but there are groups that have common factors. If I take a look at the first term here, you should see that there's a cos squared y, and if you move to the right, you'll see that this term also has a cos squared y. So what I could do is factor by grouping. I could take out a cos squared y and just see what happens. I could do the same thing with the second term, which has a sine squared y, and the last term, which also has a sine squared y. What I'll do now is just sort of rewrite the problem. I think it's just easier to group these things together based on their similarities. So I'm taking the first term, leaving it where it is. I'm going to take this guy and swap them. So I should have plus sine squared x, cos squared y. That's this guy, which is now here. This one's going to be here. So I have a sine squared x, sine squared y, plus the last term, which is cos squared x, sine squared y. This is just the left side of this problem. And like I said, the first two terms have this cos squared y in common. So what I'm going to do is I'm going to take those and I'm going to common factor them out and place them in front of a set of brackets with whatever's left after the common factoring inside that set of brackets. So when you do that, you'll see that you end up with something like this. And you can check if I redistribute cos squared y back into the brackets, I end up with what I just had. I'm going to do the same thing for the second two terms, but this time I'm going to common factor out that sine squared y that exists in both terms. And when I do that, I end up with a sine squared y on the outside of the brackets, and on the inside, I have a sine squared x plus a cos squared x. Now, if you are up on trig identities, you should be pretty excited right now, because what you're going to see is this guy right here goes to 1. That's because that's the Pythagorean identity. The same thing is true for this one. Sine squared plus cos squared is 1. So both of those guys essentially disappeared, and what I'm left with is just a cos squared y plus a sine squared y. And again, if you're up on the Pythagorean identity, you should know that that is also the Pythagorean identity. So this should also be equal to 1. As you can see, the left-hand side equals the right-hand side, and this insanely obnoxiously complex looking trig identity problem was really not that bad. Turns out it was just dressed up in some common factoring and some Pythagorean identity work. If you've seen another obnoxiously complex looking trig identity problem that you'd like to see solved, leave a note in the comments and I'll be sure to check it out. Thanks for watching.